All right, first of all, note that in this really last-minute video lecture that I'm starting at section 3.2. The reason why is 3.1 is quadratic functions and their models. And so that is prerequisite material. You should already know that. If you really need to read through that, you can. I think I have a few problems on the homework for that. But for the most part, I think you should be able to survive just fine without that me lecturing on that section. In fact, even with this section, polynomial functions and their graphs, you should be okay. If you have the prerequisite course, Math 335, then you're really going to be fine on this. This is should be something very familiar to you. Real quickly, you should recall that a polynomial is any function of the form a sub n x to the nth power plus a sub n minus 1 x to the n minus first power plus, and then you just keep decreasing powers all the way down until you get to a sub 1 times x to the first plus a sub 0 with no x on it. Notice that the way that we commonly write this in mathematics, the powers match the subscripts for the coefficients. Anyhow, also I should note, n here is an element of the natural number system, so that all these powers in decreasing order are positive integers. Okay? And then graphs of polynomials. First of all, I should say domain is all reals for polynomials. And the range just depends upon the polynomial you're given. And let's go ahead and break this apart. And I just want to show you kind of just kind of what graphs of polynomials look like. They're very smooth. They can have some wavy behavior to them. For the most part, they tend to be very smooth, lazy graphs. Okay, and they either tend, well, I just wrote 3 there, but that all have the same behavior. So let me write one with not the same behavior. So you look at that last one I wrote there. The end behavior is what happens at the ends of the graph. That's what we call the end behavior. Okay. And that's very important in calculus. In fact, because I'm missing tomorrow for my calculus class as well, they're actually using polynomial graphs tomorrow. So the same day that I'm missing for you guys. And so they are relying upon a lot of this information because they need to work with end behaviors for their functions. So all of these are end behaviors. And the way we note end behaviors, I'm just going to flip this over to talk about end behaviors. So let's suppose that you're given a graph of a function. It looks something like this. That's a polynomial. Okay, I'm not putting an x or y axis on there. That's not important to me. But what we would say is that the limit as x goes to positive infinity, so as we allow x to run to the right-hand side of our polynomial, is equal to positive infinity. In other words, as x goes to the right, the y values keep rising and rising and rising and rising. That just means that's what that notation means. As x goes to the right to infinity, the values for the function go off to infinity as well. And the left end behavior of this function would be the limit as x goes to negative infinity of p of x is equal to negative infinity. In other words, the y values dive down as x goes to positive infinity. And you could have something like that. I drew something like that a moment ago. And so in this case, both the y values on both ends are diving down. So you could say the limit as x goes to plus or minus infinity of your polynomial is negative infinite. Okay, those are end behaviors. Very, very, very important for graphing polynomials. And so let me showcase kind of an idea here. The behavior, graphical behavior, end behavior in fact, and I'm kind of glossing through a lot of the theory here because this should be a review for you, but end behavior of a polynomial, if I would spell polynomial correct, is determined by the lead term. And the lead term for a polynomial is really the term with the highest order power. So for example, p of x is equal to, let's say somebody wrote this completely wrong and they said negative x plus 3x squared minus pi times x to the 7th plus 1.8 x to the 4th minus 2x to the 10th. Well, the lead term for this, even though this is written incorrectly, the lead term is the highest power term. This term right here is the lead term. That is going to be what I call the biggest bully on the block. It's the one that as x gets very large, it takes over. Everybody else takes a back seat to that term right there. And so the behavior and behavior of this specific function is going to match. So we'll match y equals, I don't really care about the 2, I care about the negative, but not the 2. So it'll match the behavior of negative x to the 10th. The 2 doesn't really matter. Even if it's 1/1000th in front of it with a negative, I would still only care about the negative and then x to the 10th power. And I happen to know that every even power looks just like, or similar to, I should say, a parabola. It really doesn't, but it looks close enough in the big picture that I know that at the edges of this graph, it will be going like an upside down parabola, right? Like an upside down x squared, except for it's an x to the 10th, but whatever. The stuff in between is really where we spend most of our time. What does this graph look like between those end behavior points? Okay. You should also note, excuse me, so even functions like this, and by the way, when I say even, I don't mean that this whole polynomial has to be even. I just mean the lead term has to be even. The even functions like this have end behavior that's symmetric. Down, down, or up, up if that was a positive x to the 10th. Whereas odd functions, so I could, or I should say lead terms that are odd. So if I created a different polynomial, p of x is equal to, let's just keep it like an 8x to the 17th minus x plus 1. Okay, that as a polynomial is not odd nor is it even. Okay, I should state that. Yeah. However, the biggest bully on the block is this guy right here. And so when I graph the end behavior, just the end behavior of this function, it'll act like y equals x to the 17th. And really, that's just like y equals x cubed, honestly. Everything's in polynomials are based on either the square or the cube as far as end behaviors go. So I happen to know that it's not really x cubed, but it behaves like x cubed. And so I know that starts low and goes high. Again, I still have no idea of what happens in the center, and I would not be able to know with this function very easily, but we can at least do some investigation into how the middle parts look. So a couple other things I want to mention before we dive too far into this material. And we don't have a lot really to deal with, but just in case. So things that aren't polynomials. So one thing you should know about polynomials, they're continuous. Polynomials, I'll just write polys, are continuous. That means that at least at this level of course, so before you get to calculus, a continuous function is a function where you do not lift your pen when you draw it. Now, that's actually not true. There are some very cool theoretical examples where you can lift your pen and the function is still considered continuous. They're very, very highly theoretical examples, and those are the ones that we pick on. However, polynomials, even though they're continuous, do not have cusps or kinks or corners. And those three terms are very important in calculus. In calculus, you end up running into polynomials, or not polynomials, but functions that have kinks or corners. In fact, I just did a video for my calculus students that had a function that looked like this. Okay, that right here is called a cusp or a corner or a kink. It means all the same thing, really. So this would not be the graph of a polynomial because it has that real sharp edge to it. In fact, you know that the absolute value of x, which graphs out like that, is also not a polynomial because it has that kink right there, or that corner right there, whatever you want to call it. Okay. So not only are polynomials continuous, but they have a graphical behavior that's smooth. So let me say polys, as far as graphs, are smooth. They may not look smooth sometimes, and that's only because of the scale with which you're graphing them. But for the most part, they're very, very smooth graphs. Now, a little bit of theory before we jump into actually graphing, giving examples of polynomial graphs. So a theorem here, this is going to pay us back in the long run. So if P is a polynomial, and again, I'm just going to use the kind of shorthand poly, and C is an element of the real number system, then the following statements are equivalent. So the following are equivalent. Sorry, I'm not going to edit this video to shorten it or anything like that. I'm just kind of in a hurry. So first thing, if you happen to know that C is a 0 of P, I'm going to underline that word 0. We know that word 0, if I tell you that I have a 0 of a function, that means it hits the x-axis. So for an example, this point right here, and actually technically that point right there, those are zeros of, this is not a polynomial, but they're zeros of that function. Okay? Just like where it hits the x-axis there, that's also a 0. Okay. So another way to call something a 0 is that x equals C is an x-intercept, which is exactly what I was just saying, of P. Okay. Another one that we start kind of merging graphing and our equation solutions would be that x equals C is a solution of P of x is equal to 0. That is a fancy way of, a long-winded way, honestly, of saying that P of C is equal to 0. So if I tell you that 5 is a 0 for a polynomial, you know three things now. 5 is a 0 of that polynomial. 5 is, x equals 5 is an intercept, an x-intercept of that polynomial. And then if you were happen to have plugged 5 into the polynomial, it gives you an output or a y value of 0. All those should make sense that they are the same thing. The last one is more of an interesting side effect of all this. X minus C is a factor of P of x. And this one right here is actually the one we focus on quite a bit. X minus C being a factor. So if somebody says that 5 is a 0, for example, a simple example here, let p of x equal, I'm just making one up, x squared minus 25. Okay. I hope you understand that p of 5 is 0, right? Because if you were to square 5 and then subtract 25, that turns into 0. Also, you should understand that that would imply that 5, 0 is a point on the curve, or in other words, 5 is an x-intercept. Actually, technically, 5, 0 is an x-intercept. Also, I'm just going to go through this list. We would then say that 5 is a 0 of our function of p. But lastly, and this is very important, if you take a look at p of x, if I were to factor that function, it is actually x minus 5 times x plus 5. And look, x minus our 0, x minus 5, is actually a factor. And that should make sense, because if you were to try to plug 5 into this, and if plugging 5 in turned that polynomial into 0, then x minus 5 has to be a factor of that. I mean, look, if you plug 5 in, that's what forces this to be 0, 5 minus 5. So, again, all 4 of these statements are identical statements, kind of phrased differently, and the most powerful of these statements is this 4th one right there. Very, very powerful, powerful statement. And kind of a subtlety, and I'm going to mix in a little bit of calculus here while we're at it. There is a theorem in calculus called the intermediate value theorem. Very easy theorem to understand, actually, in calculus. Just basically says if you have a continuous function, and remember for our discussion, a continuous function is a function that I do not lift my pen to graph. Now, that's actually not true always, but let's just pretend for our purposes it is. The true calculus theorem says if you have a function that goes from a negative y value to a positive y value, and that function was continuous, so I had to draw it without lifting my pen to go from this negative y value to this positive y value, then at some point there must have been a 0. In other words, at some point there must have been an x-intercept. Okay, that's the intermediate value theorem, and if you read the text, there's something very similar that the author mentions here, the intermediate value theorem. And it's not important right now for you to memorize the language more, but it is more important for you to understand the implications. The intermediate value theorem for polynomials, I should say, for polynomials. Okay. If p changes signs on the interval, let's just say a to b, so you have some interval from x equals a to x equals b, some interval there, and it changes signs, p went from negative to positive, then there must be, or there exists, point C in that interval from A to B such that P evaluated at C must be 0. That should be very obvious, right? There's a point C, that point right there, the x value of C, where P at C definitely is an output of 0. Okay? So that's the intermediate value theorem for polynomials. Now we're going to go ahead and move into the next part of this. Sorry, I'm just looking at examples here. So let's do an example for graphical purposes. Let's see. Example, let's graph. I'm going to give you one that's actually pre-factored. I'm going to graph p of x is equal to x minus 2 times x plus 1 times x minus 3. So the idea for graphing polynomials is that, one, you need to first notice the overall major power. In other words, what would be the power? If I were to multiply this out, which I don't want to, but if I were to multiply this out, what would be the highest degree term? So this is roughly, it's not exactly, but it's roughly equal to x cubed, right? X times x times x. That's all I need to know, is that it has this end behavior. So I know that if I were to graph this, the end behavior, I should probably just call that EB, huh? But the end behavior is y will go to positive infinity as x goes to positive infinity. That's another way of writing what we were writing before. Y goes to negative infinity as x goes to negative infinity. And that's just a fancy way of writing this notation. Whoops, you can't see what I drew there, but I drew this. Okay. So it has that end behavior like a cubic function. But again, like I said, in between is what's the important part. And in between, I can see here from the given function, x minus 2 is a factor, thus 2 is an intercept. X plus 1 is a factor, thus negative 1 is an intercept. And so I kind of look at it as it's the opposite sign of that, right? So x minus 3, that's a minus 3, so the opposite sign would be a positive 3. So 3 is also an intercept. It's what turns that factor into 0. So I'm going to plot those intercepts. Here's one at negative 1, then one at 2, right? And then one at 3. And I'm not really being super exact with where I'm placing these. I just want to showcase this. And so here is a good kind of rough idea of what the graph might look like. Notice that as I come through here, if I'm really going to keep this graph smooth, I will completely miss that arrow right there. That's okay. I use those as guidelines to kind of help me understand how the graph is going to look in the long run. But really, it's okay for you to erase that. This is a pen, so I always work in pens. It's just a bad habit I have. But anyhow, it's a good guideline to showcase kind of where you're going to go in the long run. All right. So this brings up a question that maybe you have, maybe you don't, maybe you already know all of this. Okay. But how did I know that? I mean, we could all agree that the x-intercepts are definitely 3, negative 1, and 2. 3, 2, and a negative 1. But how did I know that it came down, came back up, went back down? I mean, how do I know about the shape of this? And the answer is very, very simple. With zeros of a function, the look of the function locally, that means if I zoom in locally just here, maybe I could do that. Okay, if I zoom in locally, it will act just like the power of the factor. So that 0 there occurs at 3, and it comes from, hopefully that comes back into focus, there we go. It comes from this factor right here, the x minus 3, and notice the power on that is 1. That means that's a linear factor. So that means that if I were to zoom in close enough to that 0, my camera won't zoom nicely to that. But if it could, it would look like a line going through that because it's a first power 0. So I'm going to write that down because I think that's incredibly important. So, and the word is multiplicity. So I'm going to go ahead and first define multiplicity here. Multiplicity. And again, you likely already know this from your previous course, but a factor has multiplicity k And the root is said to be of multiplicity, is said to be of multiplicity k. Sorry that I should type, right? That'd be fast. If the factor has power k. All right. So, as a simple example, if somebody said p of x is equal to x to the fourth times x minus 1 to the third times x plus 5, okay, we would say that there's a zero right here actually. The zero that's associated with this factor is x minus 0, or sorry, the factor. This factor is x minus 0. So we would say that 0, because x minus 0 means that 0 is an x-intercept, has multiplicity 4. 1 has multiplicity 3. Or some people will say is a root of multiplicity 3. And like negative 5 is a root of multiplicity 1. That's my dog shaking her head. And often I will just make a little table, root versus multiplicity, because it's just faster to do that. And I will say, okay, well, 0 is a root, multiplicity 4. 1 is a root, multiplicity 3. And negative 5 is a root, multiplicity 1. So multiplicity is very important, not only with polynomials, but later on with rational functions, because if you have a root of multiplicity k, then the behavior near to that root, so as we look locally, and again, this is going back to this previous page here, if you look, this is a root, 3 is a root of multiplicity 1, so is negative 1, so is 2. Okay. And if you look locally at those roots, or at the behavior of the graph at those roots, they're linear. So that is going to be the kind of the idea for helping us graph, which is theorem. The local behavior of P, and I'm using P specifically to always talk about a polynomial. So the local behavior of a polynomial about a root, we'll call it C, with multiplicity K. I know, a lot of letters there, right? So we have a polynomial. We have a root C, for example, this previous polynomial that we worked with up here, we have a root at 0, has a multiplicity k, which is 4 for that one. Okay, so the local behavior of a polynomial about a root with multiplicity k is, how do I want to say this, is of the form y equals x plus or minus x to the kth power. So it looks like a parabola or a cubic locally, or if k was 1, it looks like a line locally. If k was 12, it would look like a really flat parabola, which reminds me that you should already know the following, but I'm just going to still say it in my notes here because I think it's incredibly important. So I'll write as an aside that you should already kind of know this from your Algebra 2 class, but if you have y equals x squared, we all know that's a nice smooth parabola, right? That's okay, everybody knows that. But if you start increasing that even power, what happens is that between 1 and negative 1 on this x-axis here, between 1 and negative 1, the y values get clamped down a little bit. They kind of get smaller. They get squished. So like y equals x to the 8th would look like this. So here's 1, here's -1. Okay. And then it would be really squished down there. But then all of a sudden at 1 and at -1, if you look at that x to the 8th, at 1 and -1, that's a y value of 1. So at 1 and -1, it'll want to jump up here very quickly. And then it fires up to infinity. It still has that real parabolic look to it, except it's flatter in the center. And that is critically important to me. And that behavior, by the way, is mimicked by odd functions as well. So if you had y equals x to the 7th, we all know odd functions kind of go through -1 and 1 like that. Not all odd functions, but like y equals x cubed has this nice kind of smooth look to it. However, the higher the odd power is, the flatter it is in between, and then it rockets down. Okay, so notice how flat that is. It's not super flat, but it's pretty flat. Okay, so I wanted to mention that as an aside because you should know that, but it's still important. All right, but what I'm going to focus on here is this theorem that basically says if I give you any polynomial now, and which I will on an exam and quizzes, if I give you any polynomial and the power of that, maybe of one of those roots, is a 4th power or an 8th power or something like that, you had better draw something somewhat flat near that root. And so I'll showcase that as an example here. Okay, sorry about that. I ended up making a mistake on the example that I just did, so I edited it out. Anyhow, let's go ahead and create a polynomial just to get a single example in here. The polynomial will be a -pi times the quantity. Actually, let's sneak in -pi times x to the, let's put a 4th on there. And then we'll do maybe a 3 minus x, just to mess with you, raised to the 5th power. Let's do an x plus 7 raised to the 3rd power. Let's do an x minus 12 raised to the 9th. And finally, let's do a -x minus 12 raised to the, let's see, I have 3 odds. Let's do another even here. Let's do the 10th power. Now that's a ridiculous polynomial. And if you try to use Desmos for this, it would be completely just an absolute mess. You wouldn't even be able to tell what this looks like. But luckily by hand we can. So the first thing I'm going to do is mention the end behavior of this. Okay, the end behavior of this polynomial. So p of x, it acts like, it's not exactly equal to, but it's sort of congruent to is one way you can think of it. It's like a 4th power of x times a 5th power of x times a 3rd power of x times a 9th power of x times a 10th power of x. Now there are some things that I need to mention here that are not exactly true, but for now I'll say that. 4th, 5th, 3rd, right? So that'll be 9 plus 3 more is 12, plus 9 is 21, plus 10 is 31. So it's sort of like x to the 31st. Now I have some sign issues here, but let me just do my math again because that's actually where I messed up before, was where I had to edit out. So let me add it backwards. 19 plus 3 is 22, plus 5 is 27, plus 4 is 31. Yes, we're okay. Now I have to worry about the sign, the lead sign. Now I don't care about the coefficient, just the sign. Well, here's a -x, but it's going to eventually be to the 10th power. Negatives to 10th powers, or even powers, sorry, are positive. So this is a positive coefficient eventually. That's positive. That's positive. Here's a -x raised to the 5th through a bunch of multiplications will be a negative quantity -x raised to the 5th eventually. So this is going to be a negative. Positive, positive, positive. And then finally we have a lead well, by the way, this is also positive, right? It's just a positive x to the 4th, so positive there. But the lead coefficient is negative. Right? This is just my way of kind of keeping track of things. And so if you do that, all the product of positives is positive. Times that positive will be positive as well. Times a negative will be negative. Times a negative will be positive. So it's just like a positive. And then I quickly note that means it's going to be up, up. In other words, it's like, oops, no, it's not going to be up, up because it's an odd power. It's going to be down, up. It's like an x cubed in a way. Okay. So it starts low, goes high. Regular old positive x cubed behavior. Then I go through and I mention the roots and their multiplicity. And then I'm also just, I don't expect you to do this, but it's, I'll say root. It's for your benefit that I'm doing this. I'll mention the root, its multiplicity, and I'll say behaves like. Behaves like. And that behaves like, really, I mean behaves locally like, based on our last theorem. So the roots here, going left to right. The root for this guy, x to the fourth, is just 0. That's the thing that'll turn that into 0. And that's multiplicity 4, so it behaves locally like x to the fourth. The next one, 3 minus x, what will turn that into 0 is 3. So the root is 3. Its multiplicity is 5, right there. And so therefore it behaves like x to the fifth, again, locally. I should mention it behaves locally like x to the fourth and x to the fifth, but it might be negative x to the fourth and a negative x to the fifth. I just don't know yet. Let's see. X plus 7, so a negative 7 will turn that to 0. And that's multiplicity 3, so it behaves like x cubed locally, possibly plus or minus, who knows. X minus 12. 12 is the 0 there, and it is multiplicity 9. So it acts like x to the ninth. And finally, this one here, I'm just throwing a wrench at you. What would turn this factor, negative x minus 12, into 0, you could just do negative x minus 12 is equal to 0 to find out what turns it into 0. And you will find that that is x equals negative 12. So negative 12 is a root of multiplicity 10. And it acts locally like x to the 10th. That's an exponent of 10 there. All right. Now I'm going to plot these points on the real number line. You can see that right there. Let's see. 12 and negative 12 are our most extreme roots. So here's 12, negative 12, and I'll put positive 12 all the way over there. Therefore, halfway in between will be my y-axis. Okay. And now I'll plot the other ones. Like a negative 7 is slightly here. Negative 7. Positive 3 is probably right about there. And 0. Right about there. Okay. 0, 3, negative 7, 12, negative 12. Yes. Good. And I happen to know that the end behavior looks like it starts down and goes high. So I'm going to start it. I work left to right here. So I'm going to start down and have this graph. Oh, you don't see that. Sorry about that. I'll have this graph climb to hit x equals negative 12 there, where it's going to behave like x to the 10th. So x to the 10th is a really flat parabola. It hits, but it acts like a very flat parabola there. So notice how I did that. I first drew the behavior, the local behavior, to be a very flat parabola because, again, at negative 12, it behaves like x to the 10th. We didn't know if it's positive or negative, but because it started low, it definitely was a negative. Then it's going to just fall for a little bit and then want to be drawn back to x equals negative 7, that root. And at x equals negative 7, it acts like x cubed. So at x equals negative 7, it acts like a nice cubic. I'll draw a nice cubic through x equals negative 7. Notice how I do that, that I draw, as I'm heading toward the root, I skip forward and draw the behavior at the root. And it climbs and it wants to fall back down. When it falls back down, remember our next root is at x equals 0. And it's going to behave like x to the fourth there. So let me go ahead and draw an x to the fourth. It's a little bit parabolic, actually, not as flat as x to the 10th. And I'm going to, this is not going to be totally accurate because the y values are going to be really massive. But what I'm going to do is just quickly turn it back around to get down to x equals 3. And at x equals 3, the multiplicity is 5, so it acts like x to the 5th. So let me draw an x to the 5th there. It's a very flatter, that I should say, cubic. So notice I'm kind of under-exaggerating the y values. The y values there actually will be skyrocketed, but there's no way to be able to, I mean, I don't want to say no way, but it's not very convenient to draw it by hand accurately. So anyhow, dives down and it comes back up. And at x equals 12 here, the behavior is like x to the 9th. So that's, again, another very, very flat cubic locally. There's not really going to be a sharp edge there, but it does look sharp. It's going to look sharp. Even on Desmos, it'll look incredibly sharp, in fact, on Desmos. But this is how you would normally graph a polynomial given a factored form. If you're given a polynomial that's not factored, then you have a little bit of work because you just have to factor it. And at this point, in this section, 3.2, everything is going to be factorable. Okay. Now, a couple things I need to mention here before I exit this video. You are really verging on calculus here. In this specific example, I can see calculus that I've just taught my calculus students. So I want to show you the calculus as well. Let me get out a nice color pen here. Well, let me drop a pen. I think I'll do that first. Okay. So this point right here, this point right here, that point right there, this point right here, this point right here, this point right here. Those are all very special points. Okay. I'll draw arrows at them because they're kind of hard to see. All of those points are what we call local extrema. These are local extrema. That's a plural for local extremes, really. They're local extrema. So like this guy locally, if I were to zoom in, which I can lift the paper at least to zoom in, locally, that is what I would call a maximum. So that would be a local max. And this guy right here is a local minimum. And therefore, this guy is a local max. L max is what I start using instead of local maximum. And this guy right here is an L min. That's an L max. This guy all the way down at the bottom here is an L min. Now, I dislike teaching something without describing the importance of teaching it. So let me tell you, everything that you're learning in this video is incredibly important in calculus. The whole point of calculus, honestly, is for engineers and physicists, and you're really trying to optimize situations. I want to find, this is not going to sound like physics or engineering, it's going to sound like business, but I want to find the maximum profit for my business, or I want to minimize costs. So these points are incredibly important. In business, easily seen. You also, for physics, you might want to minimize the amount of noise in a system. In engineering, you might want to maximize the strength of maybe a building. That's a very common example, or a bridge. So anyhow, maximums and minimums are incredibly important. And we want to find them in calculus. They're very important for us to find. And it turns out, we talked about derivatives in this class. It turns out that the maximums and minimums occur when the derivatives are 0. There's also other places where they can occur. So, but for now, I'm just going to say they most often occur when the derivatives are 0. So that's a visualization of local maximums and local minimums. I should do one final statement here and give the actual true definition of a local maximum and a local minimum. I'm only going to write down the actual definition of a local max because you should be able to define a local minimum along the same lines. Okay, so f is said to have a local maximum at C if f at C is greater than or equal to f of x for all x near C. Now I'm leaving out some of the calculus notation there because you would definitely have some calculus notation here, but this should make sense. F is a local max, or f has a local maximum at C if the y value at C is at or above all other y values locally. That's really what it means. Okay? If it's a local minimum, then f of C would be less than or equal to f of x for all x near C. Okay? Now, as far as any other things, there's one minor but still mentioned theorem in your textbook, and it is actually important in calculus, so I might as well just say it here. If you are given a polynomial, and it is, let's say, nth degree, then the graph, I'll say it that way, the graph of P has at most n minus 1 local extrema. Now that's a weird statement, but I'm just going to bring back our last graph to kind of showcase something here. Remember, wherever you have a local max or a local min, it's called a local extrema. So this polynomial was degree 31. So at max, it would have 30 local extremes. That's at most, but it only has 1, 2, 3, 4, 5, 6. That doesn't run counter to the theorem. The theorem says it will have at most 30, one less than 31. But it doesn't need to have 30. It can have less than that. That's totally fine. If you think about a polynomial like y equals x squared, that has one local extreme. It's power 2. It has one less than that power for a local extreme. If you look at y equals x cubed plus x squared plus x plus 1, now I'm not telling you, actually I think there should be a minus in here. I'm not telling you this is exactly what this graph is going to look like, but it looks something like this. That is a third degree polynomial, and it has 1, 2 local extremes. So it can have up to one less than its power. Try to fit one more local extreme in there. 1, 2. Now try to fit a third one in there, and it requires a turn. And all of a sudden that turn creates not a third degree polynomial, but now a fourth degree polynomial. So there's no possibility for that. Anyhow, so that's all of section 3.2. I am sorry that I'm not on campus. I tried to put this up as soon as possible once I found out that I couldn't make it in. But please read section 3.1, or at least peruse it. Most of it you should probably know. And then just start tackling the homework. Remember, the study guide is up for your upcoming exam on Friday. So please study that. I'll be in on Wednesday.